Hi, everyone. It's my great pleasure to give this presentation to our colleagues in China. The title of my presentation is Ocean of Data, an ecosystem integrating quantum mechanics, machine learning, inverse design, CALPHAD, and experiments. My name is Zi-Kui from the Pennsylvania State University. I started my presentation by discussing the concept of entropy. We all know that entropy is multi-scale. And also it drives the world through the second law of thermodynamics. Stephen Hawking wrote a book, brief answers to the big questions. He discussed the entropy of information, the entropy and information of black hole. In another book I read, The Order of Time, it mentions that entropy drives the world. And also, time slows down when moving faster. A few years ago, my colleagues and I wrote a paper discussing the multi-scale entropy and its implications to critical phenomena emerging in behaviors and information. For any system we're studying, and we do measurements in a certain time and spatial scale. In this case, we can divide the system into different configurations from 1 to m. And this m different configurations will give an entropy we call a configuration entropy at this scale, which is equal to kb, the Boltzmann constant, times the summation of the probability of each configuration times log of that configuration, probability of that configuration. The energy, the entropy of the system is thus written as the summation, the weighted sum of the entropy of each configuration and the configuration entropy among the configurations. That's two terms here. However, we also know that each configuration itself has sub-configurations. And then that configuration, the entropy of that configuration can be written as in the same format. So the configuration of each sub-configurations entropy and the summation and the configuration entropy of those configurations. So that means we can continue to divide the system to smaller configurations, smaller scale. And we can also, of course, have to go up to the higher scale too. And in that case, we talk about the boundary condition for the system, how the system interacts with outside, with its surroundings. And with this concept, we were able to explain why the volume of the system sometimes decreases with the increase of temperature. We present our method discussed on previous slide called Zentropy approach. Zen means multi, many, Zentropy scale. It's also the partition function represented by Z. So now, as I mentioned, entropy is part of thermodynamics. And Einstein once said, the law of thermodynamics is the only physical theory of universal content, which will never be overthrown. That's because we talk about the fundamental nature, fundamental laws of the nature. And I would like to really, as this book is fun, we talk about kids, baby loves thermodynamics. Well, it's actually, the kids are natural, so they produce entropy all the time. They make a room mess and so forth. Now, we also often heard that the thermodynamics is for equilibrium only. Is that really true? But if you look at the first law of thermodynamics, it's not, right? Because it never says that the system has to be equilibrium. It only says that the heat, the work, and the mass would be exchange between the surrounding system will be balanced by the internal energy change of the system. So whether the system that equilibrium or not is not defined here. But however, when Gibbs applied it to thermodynamics, he was interested in equilibrium only. So his equation shown here, which is in almost all textbooks, is for equilibrium system. So what the difference is that it's entropy production. the entropy of reduction by the internal process. When it's not zero, then it's not equilibrium. When this one equals zero, then it's equilibrium. Then we can also do the same combined law for use Gibbs energy. Then again, we get this term here. So this term dictates whether the system is at equilibrium or not. So that means if we want to describe non-equilibrium states of a system, then we have to include this psi as a function or as a variable of the Gibbs energy. That means the energy of the system will not only depend on temperature, pressure, and the mass, but also depends on the state of the system. So psi here is the internal state variables. Okay, so that's actually the power of the CALPHAD modeling. CALPHAD modeling is to model the Gibbs energy of individual phases as function of temperature, pressure, composition, and the internal degree of freedom. Of course, when you do experiments, most times we measure equilibrium state, so this psi becomes a dependent variable. It's not independent anymore. However, when we talk about the derivatives of the energy, it could be intermediate variable. For example, we can undercool a liquid, right? We can measure the metastable states. So that gives us internal degree of freedom. However, when we measure equilibrium, this term is zero, so psi becomes a dependent variable. So we need both sets of data to develop a Gibbs energy function of the system. That's the power of CALPHAD modeling. It can deal with non-equilibrium state. So we start with the pure element and binary term and multi-component systems. So we can build up a multi-component database, as many of you are using. That's 20, 30 element thermodynamic database is available. With that database, you can start the equilibrium calculation for material design. You can do equilibrium calculation. You can calculate driving force. You can talk about the physical chemical properties through the first and second derivatives. For example, heat capacity is second derivative, and entropy is first derivative. Now we talk about the future of the materials. Then we have to mention about industrial manufacturing 4.0. Okay, so we know that we have the industry manufacturing materials 1.0 to 3.0. We talk about steam power, electricity, and computerization. So the industrial 4.0 is really about digitization. The digitization of the cyber and physical systems integrated together through digitization. Of course, then we have to talk about manufacturers 4.0 because you have to manufacture all the materials we need in the physical systems. So the digital information from all steps, from materials processing to the final products. And of course, then we talk about the materials 4.0. So we have to basically put it digitize for the material, all the materials knowledge we have. So that's the core of the Material Genome Initiative and the integrated computation materials engineering. And last year, I wrote an article about the Materials 4.0 and the Material Genome Initiative. So digitization of knowledge. What do you mean by digitization of knowledge? For the manufacturing point of view, you talk about the process material to form products to serve different functions. So in this process, you change materials. You change materials from different states, liquid, solid, vapor, or different crystals, right? So that involves phase stability. So from the materials point of view, we talk about the knowledge of phase stability and their functionality. So if you go back to thermodynamics, we talked about it before. That in 1870s, Gibbs developed the combined law of thermodynamics. He introduced the phase diagrams. And then 100 years later, Larry Kaufman digitized the thermodynamics by introducing CALPHAD method, the free energy minimization, the free energy model of the free energy of individual phases. And 50 years later, today, CALPHAD is a base for computation material design. While next 50 years, that means you will digitize more knowledge, so we develop more efficiently develop our digital knowledge of materials. So that's what CALPHAD. CALPHAD is really supporting ICME and MGI. So as you may know that, I coined the term material genome in 2002 inspired by the Human Genome Project and CALPHAD. And there was a paper published in China about my perspective on the material genome. In 2004, there was a report, publication by National Research Council, an accelerated technology transition, bringing the value of death for materials and processes in the defense system. And 2008, there's an integrated computational materials engineering ICME. It states that CALPHAD software is arguably the most important and perhaps the only generic tool available for ICME practitioners. And then in 2011, the Material Genome Initiative was launched, and there's a paper by Gregos and Charlie Kuhlman talk about the materials genome from CALPHAD to flight. So this demonstrates that CALPHAD forms the base supporting the ICME and the MGI. So what does this really mean? That means let's look at material design. We call it inverse design. We have a performance property, where performance requirements consist of several properties. And we look at what structure can do that to the FCC, BCC, HCP, and then how we can make them, and what kind of alloy elements we can put in there. Okay, so the inverse design process of materials. And then from the science point of view, we studied thermodynamics for chemistry, kinetics for process, crystallography for structure, and defects for properties, and performance. So we do simulation. Okay. Now, if you look at this kind of thermodynamics, kinetics, crystallography, what we meant, we're talking about the thermodynamics, it gives energy of individual phases. Kinetics, we talk about the diffusion, and the microstructure, crystallography, we talk about the microstructure, put the phases together, and then the defects is inside each phases, individual phases, or between the interface between the individual phases. Okay, so I give a property. So you can see that the individual phases are the building blocks of material genome. That's why I came up with the term of material genome, and also based on the CALPHAD approach, right? Because that's what CALPHAD does. It model the properties of individual phases. So when we did modeling 50 years ago, and we take data from experiments and estimations, we do the modeling. Okay. So then we do the prediction, we do the cycle, right? As you know that about 20 some years ago, and the first principle calculation became possible because the theory back in the 1960s and also the computational tools developed. And we also know that first principle calculations are mostly for 0 Kelvin, but if you add a statistical mechanics, you can do finite temperature. That's entropy. And then you can see that you take experiments, which is most for equilibrium, and the first principles can be for all configurations, then put them together, then we can develop models that have a better prediction. So it really, so you can usually start the calculation without experiment data, right? Then the experiment to validate it. So it's shifting from the experiment side to the first principle calculation side. So in this way, we developed a tool called the Dft Toolkit based on our last 20 years experience in calculations for properties at finite temperatures. So this 4 blocks here are basically the same as the materials project, but it's mostly for 0 Kelvin. So we develop on top of that a workflows for calculation of finite temperatures. So I encourage you to download, to look at the website, to install it, because it's open source. So www.dfttk.org. And also I have a paper now in the archive, you can also download it. And we know that DFT can give us the properties. However, it still takes a lot of time, right? To do calculations. Of course, experiment takes longer, but DFT calculation still takes a longer time, even with the high throughput DFT toolkit we have. So we are working on as the community is moving forward, we're working on the neural networks. So we can do the machine learning tool to develop machine learning models, so can predict the formation energy much faster than the DFT calculations. In other case, for example, we can take the existing databases calculated from DFT. Then we can train the neural network and do predictions, okay, and to get formation energy. So this you can do the cycle, get more data, right? You can do more data. So now you take so after you develop the neural network, then you can take the structure and you get the postcard file and so forth, then you can start to predict the property. Okay, predict the properties. So in that case, it'll be much faster. So we talk about the seconds or minutes instead of days and weeks in the by DFT calculation. So what it means is that you take your structure, or you can look at the DFT databases. If it's not there, you can do a prediction, which are database in the MongoDB, and it predict the formation energy for any structure you have. And again, this is web developers code. You can download it on the website. And this is our paper published in archive, still in the process to be published. And now if you think about getting all these structures, right, then you want to put them together. So we have developed a multi-property descriptor database to even reduce the time to generate the energy you need. Instead of going through all this machine learning model calculations, we pre-calculate them. For a lot of them, we have now about 4 million structures inside. And so you can easily get even faster to get the property. If it's not there, you put it in there, and then still we speed up because we have pre-calculated many descriptors. Again, this is also on our website. You can download our presentations. We're in the process to finish a paper on this database. So now we get all the data. Then we need to develop a CALPHAD databases, right? So CALPHAD database, as I mentioned before, started with pure elements, binary, ternary, and so forth. Those are multi-component databases. However, if we change one of them, for example, we change C, property of C, or the model parameters of C, we have to change everything related to C. Because those databases, these parameters are built upon this one. So that, but however, at the current practice we have, it's very difficult to go back to redo everything because a kind of CALPHAD model is one-way information flow. You take your data, you develop you assess the data, you put in the format the software uses, then you do the iteration, develop a model parameters, you get a database, you publish it. Now you want to go back to redo the work because you get new data, for example, for DFT calculations. Then you cannot do that because there's no infrastructure to put all of them together. So that's what we developed in the last several years to develop aspect tool. If you go to aspect.org, you can download the code, and it's high throughput modeling in 2 steps. The first step is called the model parameter generation. It's mostly derived from DFT calculations or the machine learning. And then you can optimize the model parameters. So you don't want too many parameters, okay? Because you'll be more overfitting. But you want the best combination of the complexity and the model agreement with the data input data. So that's called you have this kind of mathematical algorithm to judge that. And that we know that data are not actually enough to produce phase equilibrium. So in the case we refine the model parameters, use a Markov chain Monte Carlo method, and it's a Bayesian parameter estimation. And then we can, the key thing is use the phase equilibrium data because it's very accurate in terms of phase equilibrium. So after that one, we can do also the data uncertainty quantification too, okay? Because you have this statistic analysis of the data. To do that one, we need a code. We need a code for it. We need a code to do this thermodynamic calculations. So we develop a code called CALPHAD. It's just about 5-6 years ago. And it is very advanced sampling algorithms, and it uses symbolic computing, Python-based, and it can calculate the equilibrium or non-equilibrium state with independent COSI. You can also do the equilibrium calculation, of course. And the success of this code, the rigor of development of this software, made it win the run-up second place in the NASA Software of the Competition in 2019, led by Richard Otis, the developer of this code. Now, we put all the codes together, right? So it's a high throughput and uncertainty quantification. So if you go to github.com, Faces Research Lab, we have our codes there. It's all open source. And some of them not there yet. For example, Face Machine is not there yet. But we do have this codes down. You can download here. We have DFT, that's for data generation. And then we have the data processing, PyCALPHAD aspect, And we have workshops too. Okay, now we have Metagenome Foundation. It's our nonprofit organization to do the training courses. We have recorded videos on YouTube channel too. So now we go to data ecosystem. Got a proto data. Now proto data is theoretical prediction, machine learning, DFT, AMD, finite element, and also experiment data. That's very important because the experiment data are critical because you put all everything together, right? So also validate the prediction. But however, I understand the prediction cannot predict everything, but put the individual things, individual configurations, and then put them together, compare with the experimental measurements. And then when we get this data, proto data, we do a process data. So it's CALPHAD modeling. We develop CALPHAD databases, use PyCALPHAD and SPAD. All the applications is for efficient material design. And important that this can be used in situ or on the fly for dynamic manufacturing control. We call it dynamic zero scrap manufacturing. So the process can be tailored depending on what happened before. So you remember the history there. So you can always tailor the processing, make sure you're always in the optimal condition. And it now also can predict the service lifetime. And then at the end, you can do the recycle of the materials. So we wrote a paper to discuss this concept a couple of years ago, ocean of data, integrated first principle calculations and CALPHAD modeling with machine learning. 2018, we published this paper and laid out this concept. But now we have almost all the components now to put this together. And one of my colleagues at Penn State drew a diagram for this data ecosystem. Ocean of data, basically that you have different data generated by different groups, different people, and also for industry. And we hope we can access all the data together from this ocean of data and then analyze, process them to get the process database and for material design to make new materials or improve existing materials, then produce new data, and so it's a cycle. So it's the ecosystem. In this way, I wrote another overview paper to discuss this kind of fundamentals, computational thermodynamics, and also tools and its application, talk about stability, a typical phase equilibrium, and also cross phenomena. We can predict other coefficient properties like Seebeck coefficient, Sorel coefficient, and piezo barioelectric coefficients. So that's for the for cross phenomena, and also we can really predict transport properties like diffusivity and conductivity, and also even mechanical properties, so elastic, plastic, and to the stress strain behaviors. Okay, so we get all the data, right? We do material design. So what we typically do in material design is that we have the data, we have the idea, we have some hypothesis, then we do calculations, right? So that's this is our knowledge, through our thinking, to generate this possible candidates, then do simulations, then do iterations here, then do experiments. But can this process also be done through the machine learning? Oh, it is. That's one approach in the community called the generative adversary networks, GANs. But because we don't have enough data, so we have to condition ourselves by focus, narrow it down. So we conditional generative adversary networks, so CGAN. Okay, so we just wrote a paper, submitted to the Journal of Materials Informatics, the journal edited by in chief by Tongyi Zhang Tongyi. I will thank him for inviting us for this perspective paper. And in this case, we're talking about you have two steps. The first step is build up your neural network. Okay, basically build up your latent space. So connect everything you observe, right? You have to go one level down to figure out the connections. Okay. So you have to have input data. Okay. You have random properties you put together to train the system. So the system understands what's real, what's random. Okay. Then we build up this random latent space code. That's the CGAN. And so when we build up the CGAN, then we can say, okay, what property do I want? Okay, that's your design target. And you put the design goals into the system. The CGAN will search, we'll search this, we'll go through this just like our thinking. and it gives us the possibilities, not just one, right? Because it's the probability, right? It's to give a range of probability. Then we can take this probability, this ensemble of the alloys. Then we can do the simulation. Okay. Then we do simulation. We can get data back to the system, right? Retrain the system. And after this iteration, we can go to do the experiments. Okay. To get more data into the real alloys. Then you can refine the system. It's just like how we learn, right? So we and I today have some preliminary examples. We discuss this book. I don't have time to discuss here. So now with this, you can think about the 4 components, right? You got the data generation through the DFT and machine learning and experiments. Then you take the CALPHAD method to develop the databases. Okay. Then you take the CGAN to the inverse design. Okay. Then you do experiments. Of course, CGAN, we have design, you can do the computation, right? So that gives us this kind of information flow. These iterations. You got to put the data, then you process the data, then you do the CGAN inverse design. Each of them have internal. You have this. You have the internal mini iterations. But for the large iteration you have here is that you get the product data, you do the process data, you design, inverse design, and the manufacturing, you get a service, you get this kind of cycle. But of course, as I mentioned, you have a lot of smaller cycle between each, okay, between two areas here. In that case, we can really create an ecosystem for materials and manufacturing. With that one, I will thank you for your attention.